If you've ever looked up into the night sky, it's likely that at some point you've seen a shooting star or a meteor. These streaks of light across the darkness are left behind by small pieces of debris burning up in our atmosphere after colliding with our planet. But where does this debris come from? It seems to rain down from the darkness above, leaving us with more questions than answers. So let us learn about the far reaches of our solar system and discover where these celestial breadcrumbs are actually coming from. To answer this question, we are going to have to take a journey to the outer edges of our solar system and explore two icy reservoirs known as the Kuiper Belt and the Oort Cloud. These regions contain trillions of icy bodies, many of which are only a few miles wide. And when their gravity is disturbed by passing stars or rogue planets, they get flung into the inner solar system, where we can observe them as comets. But before we launch into deep space, let's make sure you're subscribed so you don't miss any of our future videos. And while you're at it, leave a like as well. As a reward for doing that, here's an adorable picture of a baby sea otter. Now let's get back to space. Unlike most objects in our solar system, comets don't orbit the sun in nice, neat circles. Instead, they follow elongated paths that extend as far out as Pluto and then wrap around the sun before heading back out again. If you've ever seen one of these paths and thought, well, that looks like an ellipse, you'd be correct. In fact, every comet orbit is an ellipse with the sun at one focus and the other focus lying somewhere on the path itself. These elongated paths are important because they tell us a lot about the history of each comet. For example, if a comet's orbit never takes it closer than Pluto, it will never pass Earth's orbit, and we woe and see it again for tens of thousands of years. However, if its path brings it inside the orbit of Jupiter, we might only have to wait a few hundred years to see it pass the Earth again. This is why astronomers divide all comets into two categories: short period and long period. Short period comets have orbital periods of less than 200 years, and most of them originate in the Kuiper Belt, a region of icy bodies located just beyond Neptune's orbit. The Kuiper Belt is about 30 astronomical units from the Sun, with 1 astronomical unit being the average distance between the Earth and the Sun. Within the Kuiper Belt, there are billions of objects ranging in size from small houses to dwarf planets like Pluto and Eris. While Pluto was once considered the 9th planet, it was reclassified as a dwarf planet in 2006, when it was discovered that there were many other objects of a similar size orbiting the Sun in the same region. Since then, astronomers have identified more than 2,000 Kuiper Belt objects or KBOs, but most of them are too small to be seen with the naked eye. However, every so often, a passing star or rogue planet will gravitationally tug on one of these small KBOs and send it hurtling toward the Sun. As the icy object approaches the Sun, it heats up dramatically and releases gas and dust. This creates a glowing head known as the coma, which is surrounded by a cloud of dust and gas called the envelope. When this material collides with particles in our atmosphere, we see it as a meteor or a shooting star. Most short-period comets have regular shapes with fairly round heads and tails that point away from the Sun. This is because as they approach the Sun, the intense radiation pressure and solar winds strip away most of their volatile ices, leaving behind only the denser materials such as rock and dust. Eventually, though, the forces of gravity take over and the debris is drawn toward the Sun until the next star passes through and kicks off another wave of comet activity. But what about those comets whose orbits extend as far out as Alpha Centauri? They take thousands, even millions of years to complete just one orbit around the Sun and are known as long-period comets. Unlike short-period comets, long-period comets do not originate in the Kuiper Belt, but instead come from a giant sphere of icy rocks known as the Oort Cloud. The Oort Cloud is theorized to begin at about 2,000 astronomical units and extend as far out as 100,000 astronomical units. To put that in perspective, it's the farthest planet in our solar system, Neptune. It's only 30 astronomical units from the Sun. So the Oort Cloud is truly mind-bogglingly distant because it's so far away. We haven't directly observed the Oort Cloud. But astronomers are pretty sure it exists based on the number of long-period comets that enter the solar system each year. The exact origin of long-period comets is still unknown, but many astronomers believe they come from the outer reaches of the Kuiper Belt or even the scattered disk. This region is home to icy objects that have been flung far out of the Kuiper Belt by the gravitational pull of Neptune or other large planets. Some long-period comets may even come from outside our solar system entirely. In fact, about half of all long-period comets seem to have orbits that were once bound to another star before being flung into our solar system by a close encounter. Comets from the Oort Cloud have highly elliptical orbits that bring them close to the Sun and then send them hurtling back out into interstellar space. Most long-period comets have irregular shapes with very long, thin tails that point away from the Sun. This is because they spend so much time in the cold, outer solar system that most of their ices remain intact until they very close to the Sun. As they approach the Sun, these ices begin to vaporize, creating a glowing coma that is often much larger than that of short-period comets. As the coma expands, the solar wind and radiation pressure strip away most of the dust and gas, leaving behind a dense solid core. This core is what gives long-period comets their distinctive cigar-shaped appearance. Once the core is stripped away, the long tail forms and continues to stretch as more and more ice evaporates. This process can take several months, during which time the comet is at its brightest. Eventually, the comet reaches its aphelion, which is the farthest point from the Sun in its orbit. At this point, the comet's tail can be hundreds of millions of kilometers long, making it visible from almost anywhere on Earth. As the comet continues on its journey, the force of gravity causes it to slow down, and eventually it turns around and begins its long journey back to the Sun. This journey can take thousands or even millions of years, during which time the comet will pass through the orbit of Jupiter, Saturn, Neptune, and finally Earth. When the comet approaches Earth's orbit, we see it as a meteor shower rather than a single comet. That's because most long-period comets break apart into many smaller pieces when they come close to the Sun. These pieces, known as fragments, continue to orbit the Sun in a swarm that remains visible for many months. Gravitational interactions with the planets can also have a major impact on the shape and brightness of a comet's orbit. For example, if a comet gets too close to Jupiter, it can be flung out of the solar system entirely. On the other hand, if it makes a close pass near Saturn, its orbit can become more circular. This is why some comets return to Earth at regular intervals, such as Halley's Comet, which has an orbital period of about 75 years. In addition to changing the shape of a comet's orbit, gravitational encounters with the planets can also cause them to brighten dramatically. For example, in 1994, Comet Shoemaker-Levy 9 had an estimated magnitude of only 17 when it passed Earth's orbit. But when it made a close pass by Jupiter a year later, its magnitude increased to 8. This brightening is known as the slingshot effect and occurs because the comet gains speed as it falls toward the planet and loses potential energy. This results in an increase in kinetic energy, which causes the comet to brighten by as much as 10 times. Now that we know where comets come from and how they evolve as they approach the Sun, let's take a closer look at some of the most famous comets in history. We'll start with Halley's Comet, which has an orbital period of 75 years and is easily the most famous comet in human history. According to legend, Halley predicted the comet's return in 1705, although his calculations were actually based on the work of a Danish astronomer named Ole Rakmer. Regardless, Halley's name became synonymous with the comet, and people began to believe that it heralded the end of the world. This belief was only reinforced in 1910 when newspapers across the United States ran stories claiming that the comet would pass Earth on February 4th and wipe out all life. As it turned out, Halley's Comet passed safely by Earth and humanity was spared. Next, we have the Tunguska event, which occurred in 1908 and is the largest known impact event in modern history. According to reports, a massive comet or asteroid struck the Earth near the Tunguska River in Siberia, Russia. The explosion is estimated to have released between 10 and 30 megatons of TNT, which is equivalent to between 3 and 9 atomic bombs dropped on Hiroshima. The blast flattened an area of forest the size of Manhattan and was felt as far away as Washington, D.C. Although no crater was formed, the impact left behind a large number of meteorites that were later found strewn across the landscape. Finally, we have Comet Shoemaker-Levy 9, which had an estimated magnitude of 0 when it passed Earth's orbit in 1993. It was the first comet to be officially designated a hazard by the International Astronomical Union and raised its hopes that we had finally found a way to deflect asteroids and comets away from Earth. Unfortunately, these hopes were dashed when the comet broke apart into many pieces and became much dimmer than expected. Nevertheless, the mission was a resounding success, because it taught us a great deal about comets and provided valuable data that we can use to protect our planet in the future. The study of comets is incredibly important, because they preserve a record of the early days of our solar system. By studying comets, we can learn about the conditions that existed when our solar system formed, and even detect molecules that may have played a role in the origin of life. Comets have been fascinating humans for centuries, and will continue to capture our imaginations for many years to come. Thank you for watching, and let us know in the comments below what you think is the most interesting thing about comets.